Okay, today we're talking about the X Mega, which, if you remember from our description last time, is like a shark with laser beam. Before we do that, we want to talk about very briefly about fuses because we kind of forgot to cover this topic. So fuses are basically little configuration options on your microcontroller. They're things like they tell the microcontroller whether its clock source is internal or whether it's using an external oscillator. One of the fuses is called CKDIV8, and it's turned on by default, and it makes the clock, it basically divides the system clock by 8. So if you think you're running at 8 megahertz, if this box is checked, you're actually running at 1 megahertz. And the funny thing is, you probably won't notice this for a while you're writing test code, but then suddenly you'll have like an LED soft PWM function, and your LEDs will blink because they're actually being updated 8 times as slow as you expect. So we're going to send instructions for how to reset or how to set fuses. It's kind of a dangerous operation to do it within WinAVR and with AVRDude because you can you're basically setting all the fuses at once, and if you have one hex bit, set incorrectly, you might basically break your chip. You will set a configuration option that your gadget doesn't like. So the safer way to do it is to, if you're using Windows, is to get AVR Studio, and there's a graphical interface for checking and unchecking fuses so that you know what you're checking. And if you don't want to download that, just come to office hours, and I think a TA will probably be able to set your fuses in about 5 seconds. It's a very fast operation. So that's the safest way is just to get it done in office hours.
Basically, on your chips, when he's saying you can brick it, what he means is you might have said, clock div by 8, you could check it, uncheck it. That doesn't break anything. What can break it is if there's a thing where you can use the reset pin on the ATtiny as an extra I/O pin. But once you do that, you can't reprogram it by toggling the reset line low anymore. So if you're making like a million of something and you've got your code down cold, no problem, get that extra pin. But if you're writing code and you accidentally change that reset line, you can no longer reset your gadget to reprogram it, which is bad. The other one that you can do is you can disable, I think, SPI programming, which means you can no longer be programming it using the ISP that you guys all have.
Or you can decide that your clock source is external. So because it's not on your mini gadget, you don't have an external clock. If you set it to be external, your microcontroller has no clock anymore. Without a clock, nothing runs. So.
And more importantly, the ISP requires
a clock
on the microcontroller to operate.
So you can't reprogram it either.
Yeah, well you can, but you have to hook up a function generator, generate a clock on some external pin, and then you can bootstrap it to where you can reprogram it, and then you take away the function generator. It's usually faster to just desolder the reset microcontroller, throw it on the floor, and put a new one. So feel free to reprogram your own fuses, but you need to do it safely. Otherwise, you'll have to visit TTAs and get a new ATtiny.
All right, so yeah, sorry about not talking about that extensively in the past.
Although, honestly, usually all we would do is people would test their gadget and be like, okay, power's on. They would come to one of our laptops. We'd wave our hands over the fuses and then say, here you go, your fuses are good to go.
Yes. If you remember the mini gadget construction, we actually did do that. Probably most of you don't remember that step. We basically did it at the same time that we programmed on the initial code to make the LEDs. All right, so that's fuses. Let's talk about X megas and tinies. All right, so here's the comparison between a relatively small X mega chip and the tiny 84. So flash memory, 8K and 32K, which isn't that much of a difference, except this is the variant of of the tiny series that has the most flash memory, and the X megas can go up to 256K or more.
That is the smallest X mega and the largest ATtiny.
So RAM also.
RAM on the X mega, I think it was 16 or 32.
Maybe even more exciting, ADC, 2 megasamples per second at 12 bits versus 15 kilosamples per second at 10 bits. Now, why do you care about that? If you want to read like speech, you generally have to sample at 40 kilohertz, 44 kilohertz, it's like CD quality. So you can't do it on a Tiny. It's not possible. On an X Mega, it's not even hard.
The X Mega also has DAC, so it can do digital to analog. So after you've read in your sound, you can then play sound output to a speaker. Like you can do real audio, whatever you want.
Not just buzzers.
The timers, the AT-Tiny has 2 timers. One's kind of crappy, one's also kind of crappy. The X Mega has 5 timers. I think it even has more than that. Like it just leaks timers everywhere.
Yeah.
And then the Tiny, there's one UART sort of, kind of does some stuff. The X Mega actually has 7 USARTs, 5 of which can be used for SPI. There's 2 I2C. If you want to talk to like 11 different digital contraptions, the X Mega works. The AT-Tiny does not work really as well.
DMA, we'll talk about that in more detail about what it is. There are no DMA channels on a Tiny. There are 2 on an X Mega. This means that you can, without involving your microcontrollers, basically the core computer of the microcontroller, you can sort of shift data from one input or output to another input or output without taking up clock cycles or CPU cycles. The Tiny can run at 16 megahertz. The X Mega can run at 32 megahertz. Notice though that they run at a lower voltage. You cannot power an X Mega off of 5 volts. You have to do 3.3 volts or less. And that's generally just a trend in all sorts of processors. A lot of CPUs and computers you can only power at like 1.8 volts or even 1 volt because lower voltage, if you remember, basically equates to lower power use.
And modern CPUs are still burning ridiculous amounts of power. The only thing I'll add here, so what this is showing you is 8-bit microcontrollers. This is
both of them are
basically,
still 8-bit microcontrollers.
it's still you're writing the same sort of code, you're not doing anything too crazy. As soon as you start saying, I want something bigger and faster and better, you start talking about the ARM core processors, Cortex M3, Cortex M4, ARM7, ARM9. And they have similar features to the X Mega, except then the clock rates just go through the roof. They have way more DMA. Interestingly, they don't have more UARTs. Like this is actually a very good feature set in terms of like twiddling things in the real world.
Which is why the X Mega is good if you want to control a bunch of real world applications. Like if you want to communicate with sensors or do control speakers or motors. And
Yeah,
stuff.
but you still want to stay in a simple kind of processor. Because as soon as you go to an ARM7 and a Cortex M3 and 4, you start saying, should I be running an operating system? And if you've taken that class, there's details in running your own operating system. And even if you're going to take somebody else's operating system that works on those chips, there are a lot of frustrating details with getting that stuff working, which is completely different. Yes, you still make program and make compile, but like the things that are happening in that make file are much more complicated than what happens in like your AT-Tiny example code. So when something goes wrong, it's much easier to fix this, especially if you just want to look some money.
I guess one last note, obviously there's more pins, but there are variants of the X Megas that also just have native USB device capability. So they would be, you just hook up the USB data transmission lines from a computer and it talks over USB native.
Yes, but again, you start writing your own USB controller.
Yeah, it's a fair amount of code to get USB right. That said, there are simple ways to handle USB, like the cable that you all got with the nice 4 pins is just a USB. It contains a USB to serial converter, so you can actually talk over USB with it to any device that has TTL serial, which is almost even the AT-Tiny has to show you the older thing. Okay, so that's X Mega versus Tiny. And like Brian was saying, there are 32-bit controllers that are even more advanced. They will find in cell phones or Raspberry Pis, but then you start running operating systems and the code gets quite a bit more complex. The tool chain of the code.
So, and what you'll find is you don't get more UARTs, you get fewer timers, you get fewer DACs, fewer ADCs as you start to get into these bigger processors. So if you have to actually run like software to like process your audio and process your data, that's what you use those for. But you still actually end up using these kind of processors to do your low-level interfacing. Even the Raspberry Pi, if you look at it, nobody actually uses the low-level I/O on it. They go buy these breakout boards or daughter boards that if you look on them, they're either an Arduino or an ATtiny, an XMega, right? Everyone avoids doing that at the computer level.
Okay, so the XMega series is a little bit more complicated, and what Atmel has done to maybe declutter their data sheets is they've created two different types of data sheets. They've created a part-specific data sheet and a manual. So the way that the part-specific data sheet is, it tells you exactly, so there are a number of XMega A series or D series or whatever series chips. The part-specific data sheet will tell you, let's see if I can get this.
And for some reason, Atmel has completely revamped their data sheet style in the last week.
Really?
Yeah, you'll see in
Like
a
it.
second.
All right, computer, oh, okay.
Across the streams. But basically, the part-specific, yeah, it will tell you if this is the data sheet for the ATX Mega 32A4. Here are all the pins. It has this super important page called the pin map page, which tells you what goes where. And then if you actually look at like, what does the serial section do? It just says, hey, it's got serial. You should probably look at the real data sheet to figure out how it works. And then what you do is you go over to the A-series manual, and inside that it has what you would normally used to see, where it's like the long explanations about the serial, and then finally at the bottom, here's the register description, here's all the registers, here's what you do with them. That's all in the A-series manual, whereas the part-specific one, it tells you exactly where the pins go, what's in the chip, but nothing about how to use it.
So the A-series manual generally, so the part-specific manual is useful when you're doing your circuit board schematic and layout for the most part, and then the A-series manual is more useful when you're doing the actual programming. Now you need both at both times, but just in terms of how long you'll be staring at each one. When you're programming, you'll mostly be staring at the manual.
Basically, when programming, you will say, okay, I hooked up this accelerometer to this SPI port. It's on pins PA3 and PA4 and PA5. Which one is that? And then you go to the pin map, you say, oh, that was SPI2. So then you go to your code and you just, everything is about SPI2. And that's the only time you use it. All right, that's still angry?
I don't know, I think this, is this it, or is this
Looks
somebody
like
else's?
this.
Yeah, this is it. I had it open. PowerPoint's still angry, but whatever. So this is the part-specific data sheet.
And
It's
they now
a
look
mere
different, but don't worry about it.
108 pages. That's the other tip-off. If it's only 108 pages, it's not giving you all the information you need. And I'm serious about that. So yeah, you can.
Do you want to show the pin map that's like this?
Yeah.
I think it's way down at the bottom.
You know.
Pin out and pin function. The only thing you need in this data sheet is a couple pages down in section 30.
So
Alternate pin functions, yes. So here they define stuff, and like the DAC pin is the DAC.
And here.
Ta-da. So when you want to
Zero,
use
okay.
analog to digital converters, you have to go here and you say, aha, ADC 0.
It's on PA0,
Yeah.
which is pin 40.
So PA0 to PA7 are ADC ports, but then you got bonus ones on PB0, PB1, PB2, and PB3. And you just have to look there to figure out where all your stuff is.
Yeah. So yeah, that's.
And then like, here's a serial port, TX and RX on USART 0 or on PC Scribble and BC Scribble. I can't read that. So I doubt you guys can either, but it tells you where the pins are.
Let's see one, yeah. Let's see.
And that's
let's
just
go
where you
over
need to
there.
be. All right. I'm trying to look that. changed everything.
Here it is. Okay, so here's the preliminary manual. It's 432 pages. I'm going to download that.
And for some
Oh,
reason, they
whoa.
changed the font with a few other things.
All right.
But it's the same data sheet.
As long as they only change the width.
Yeah,
So recommended reading, notice this, the device data sheets and also the application notes, which we're going to get into later. Those are going to be very important if you want to program, if you want to quickly program stuff. They basically tell you how to do a lot of stuff. So, okay.
So then other details, the X megas are only 3.3 to 1.8 volt parts. So you cannot use 5 volts. So some of you ended up having like sharp IR sensors that need
Yeah.
5 volts. So then suddenly you have to worry about how to interface between different voltage levels. There are really handy chips that let you just do this step pretty easily, but it's more work than just, whereas with some of you guys we said, hey, you're running with this 5 volt accessories, just run your processor at 5 volts, easy. Or, oh, you have a 3 volt accessory, just run your part at 3 volts. And like, you don't have to worry about interfacing between them because you just make them compatible. Nowadays, it's very easy to find 3.3 volt equivalents for most things. If you have a data sheet for a part that looks like somebody photocopied it, and it's like 2 degrees off, that means you're using a really old part, and it's probably going to be annoying to interface with. Just go look for one that has a nice data sheet that was generated, this millennium. And then these arbitrary parts, we used to say they had a ton of terrible errata because like a lot of things didn't quite work right on the X Megas, but actually now they kind of do,
Yeah.
as long as you buy the newer ones. And now they have USB, which is fairly new, a couple of years, I guess.
No, the X Mega series is 4 years old, I think, when the first one came out. So
Yeah.
that's starting to be mature, I guess. Although the 18 Mega series is about probably 12, 13 years old. So. All right, so how do you program these? Basically, you're using the same tool chain as the AT-Tiny. The XMega 32A4 is even still supported in WinAVR, even though that was released almost 3 years ago. Some of the other ones, I think, some of the newer ones, you may have to use Atmel's own compiler.
So what actually happened, all of you guys are using AVR GCC and AVR libc. There used to be some guys who basically made this thing called WinAVR, or whenever, if you believe their thing where you have to say it that way. And it was just, open source tools. They would just keep it up to date and output it for people who were using Windows. And then what happened is like 2011 was the last year you could ever get a new version. And what actually happened is I think Atmel basically hired all those guys away. And now Atmel Studio 5, Atmel Studio 6, you can download them from Atmel. Buried way deep inside is the actual what it does, and it's now called AVR GCC Toolchain for Windows. It's snuck, hidden away in the install directory, the 1 gigabyte monstrosity of AVR Studio. So if you still want to use it, you still can. You just have to install AVR Studio and then change the path from WinAVR to AVR Studio / AVR GCC toolchain for Windows, and it's all the same stuff as there. And the reason you need to do that is because a 3 or 4 year old compiler does not have chips that are younger than 3 or 4 years. And frequently people find you want to use the new chip and not the oldest, crappiest chip you can find. Or if you're in Linux, you can just get the newest versions of AVR GCC and AVR toolchain. Frequently they are not whatever package you can get through a package manager. Usually those are out of date as well. But this stuff exists. You can also use Cygwin like that. But they're very different syntax. You don't use the _VB anymore. And now what it is they have a whole bunch of things. So when they want a VB, which just creates a bit mask, they now just have a thing called pin1 _BM, and you get a pin1 bit mask, which looks like a 1 and a whole bunch of zeros, whereas the pin7 bit mask is a whole bunch of zeros than a 1. So that you have a lot less of these weirdo macros in your code. There's also a bit position where the pin 3 underscore BP would be the value 3, so that when they needed to do some shifting in your code, they'd use the bit position. And then there's a group configuration where when you guys look, if you remember like setting the clock select lines for your software PWM, they had 3 pins. They had a big table explaining that you could get clock divided anywhere from 1, 8, 64, 256, 512, but you had to select these 3 bits in various sequences. Most of you just use the biggest one because we told you to. But if you actually wanted to do that, your choices in your code was to either have something that looks like random register or equals bit value, clock select 1, 0, clock select 1, 1, clock select 1, 2, and it just kind of looks ugly. Whereas with this, you could just say random register or equals clock div 0 underscore GC. And then that's your div 0, or you can have div 2024, div 8, and it's a lot more readable for people who are trying to figure out what you're doing with these little twiddly bits.
Yeah, so although it's different, it's actually better. The register setting stuff is clear. It's generally a little bit more sane. I wouldn't say it's as clear as the Arduino yet. It's definitely better than the AT.
And then you guys, I don't think at least in this class, we haven't made you write enough code to get angry at how everything is so specific, where you're like, okay, now I have to take this other port and set these pins to outputs and then these data direction lines high. Whereas they finally have structs. So there is port A, there's a port object, and you can initialize a port, and if you want another port initialized the same way, you can pass a reference to that port and do the same thing. If you have 3 USARTs that you all want configured to be 9600 baud serial, you can have one function that initializes a serial port struct. So like it's more, real programming as opposed to, if you look at an ATmega, some of them will have 4 serial ports, but all they do is they have different enumerated macros, and you literally have to make 4 init functions with different named registers and macros just to get them all initialized to do the exact same thing. So your code just looks horrendous. So it's a lot nicer out of these XMegas. And there's a bajillion of these defined. They're all hidden away. I think this is actually in our project, somewhere in like the course documents we have this, because it's a pain to find.
Yeah, that's true.
Because all of these pin group configurations, bit positions, bit masks, there's a sensible naming scheme to them, but you have to learn what the sensible naming scheme is.
The easiest way to do it is just to look through that other file.
Yeah.
Okay. So the tables for each module are in the parts data sheet. So we just showed you this within the data sheet. So you know that like pin D, if you look at this, pin D2 has a bunch of interrupts. It has a timer zeros on it. I think a USART, the RX pin on a USART. So you kind of get a sense of like what's going on each thing. So like Brian was saying, you can see there's a USART D0 and a USART D1. That basically means there's a serial port on port D, and there's actually 2 of them. There's serial port 0 and serial port 1. And what's nice is like your code for USART D0 can work with USART D1 without needing to make a whole new function. Okay, ports, are a little bit more complicated in the sense that each I/O pin now has a bunch of different configuration options. And this is actually a good thing. So most of you use like a pull-up resistor on your button to pull it down or pull it up. With the XMega, there are built-in pull-down, pull-up resistors, so you can choose to either have it pulled up by default, pulled down by default. You can obviously set the data direction to output or input. You can set and clear them. I think you can
invert the bit. If you decide that in your world, when you say 1 to the port, you'd better turn your LED on, but your LED's wired backwards, so you have to actually give it a 0. You can set the port as inverted, so that when you give it a 1, that pin goes low and your LED turns on.
Right.
Um,
There are interrupts on every port, there's interrupt levels.
Yeah, there's all kinds of just sort of crazy things. You may not need them. But what they also did is they created a bunch of identical registers that do very similar things. So for instance, there's a DIR register, which is exactly the same as your data direction register. It tells you the data direction registers. If you write to that, like you did the DDR, it'll do the same thing. But they also created DIR set, DIR clear, and DIR toggle, which also have 8 pins in them. And if you wanted to, instead of looking at your data direction for the, you could simply say, I'm going to toggle pin 7. I don't care what it is. I'm just going to toggle it. It's going to be the opposite of what it was. And you could totally do that using code, right? You could read the data direction line for that pin, and then figure out what its value is and then set it to the opposite. Or you can do complicated stuff where you read it, mask it, clear it all in one instruction. Or you can just toggle it. Or if you just want to clear it or set it, right, you can explicitly set pins. And you end up with a lot less of that weird port and equals tilde port or equals blah, blah, blah. And you could just say, DIR clear, this pin, done. And there's a lot less shenanigans. So it just looks like better code. It looks more like code and less like squirrely Qbert angry geese.
So is it, DIR A for port A or out A for port A? It's not exactly like that. There are these registers, port A out, port A here, but you shouldn't use them. Instead, what you should do is access them via the start frame. So port A has, just basically a bunch of different registers associated with it, including a direction register, a DIR set, a DIR clear, an out set, out clear. And so you access stuff by typing basically port A dot here. And then let's see, find it easier to just get to this. Or maybe,
Yeah.
all right.
Well, we can just show it real quick. So I realize not everyone's going to be using an Xmega, so most of you will be like, I don't care about this. I'm not going to get tested on it, so relax. But the code, so you guys had to do exactly this. You had to have your set output sort of business with the set LED. Now you can just say, oh, port, set it out as an output. Otherwise, set it as a clear it. Right? It's a lot cleaner looking. When you're doing really complicated stuff, it's nice that all the pieces are much simpler looking.
And notice what is being sent to this is a reference to port A. So, this is a little bit of pointer direction, but basically this becomes the same as port A dot here set equals pin 3 underscore BI.
And so for those of you who are really looking forward to doing much more complicated software, like this looks a lot more like real people software. You don't have to constantly be doing little macros. And you want to set the direction output. This will work on all ports, right? You don't need to write another function to do it.
Yeah, that's a big thing in 18 mega. If you want to make a general set output function, it's a very complicated function because you have to just.
There's 3 or 4 registers you have to hard define. Oh, it's the LED pin. Oh, we also have to define the LED port. Oh, and the LED DDR. And sometimes the LED pin, the pin of the port in register.
So clocks.
So it has a 2 megahertz internal clock. So if you do nothing, it's just going to run at 2 megahertz. But it also has a phase lock loop, and it can go up to 16 times faster. Or if you want to go some other random speed, you can do that too. 16 megahertz is great if you're going to do USB stuff. But basically, this function does some magic poking and just turns on the 32 megahertz oscillator and lets you run at 32 megahertz instead. And so what's kind of interesting is that you start up at 2 megahertz and then you're allowed to boot yourself up to 32 megahertz. And then at any time, you could go back down to 2 megahertz. You could go even slower if you wanted. So you have a lot more power control over your system. So if you're doing a lot of computation, you go into hyper mode, you hit the turbo button, and start doing all kinds of stuff very quickly. And then when you're done and it's time to sleep, you could either go to sleep, or you just clock yourself down to like 128 kilohertz and just chill out and wait until something happens.
There's also a built-in real-time clock. I think it's some X megas, which is basically like a,
That's all of them.
yeah, it's a quarter crystal type, right?
Well,
Is it
so
active?
there's a terrible RTC, but it's approximately 32 kilohertz. But what it means is that you could have this time, and then you could have like your other time. So you could have like a slow timer that's just counting up milliseconds. And you know, it's a millisecond plus or minus a little, but you could start building like a timer and start having like more operating system like stuff that are helpful. Like it's nice to say, well, I had a timeout, and this timeout is based on time and not like 32 megahertz time. Like no one cares about that. You care about did something happen within a second. If not, we do something else. And then there's also, if you're doing high-speed PWM, it actually can overclock, and you can do up to 128 megahertz. And the reason for that is that sounds really fast, but let's say you wanted to have 16-bit control. So take 128 megahertz and then divide it by 2 to the 16, and then you're left with, I think, 60 kilohertz? I don't remember, but it's not as fast as it sounds. So if you want to have really good control over something going a few hundred kilohertz or 50 kilohertz, does anyone have Google? What is the answer to
I
that?
think 2,000.
It's only 2 kilohertz? That's got to be faster.
2,060.
But anyway, it sounds fast, but it's not.
2,000.
Okay, well that's depressing.
But if you want 10-bit control.
If you want 10-bit control, you
So yeah, just to be clear, this is not the speed at which your CPU is processing things. So you can't overclock it to 128 megahertz, then calculate, add or subtract at 128 megahertz.
You can just blink
You
LEDs
can blink
up to
LEDs.
128 megahertz.
Exactly.
Or more likely, you will twiddle pins on a motor controller and get 16-bit control, speed control at 2 kilohertz, or you might get, at 20 kilohertz, you might get like 12-bit control or 11-bit control, which is still pretty good.
All right, so interrupts are pretty much the same as before. Like what we've told you about interrupts and what they do, basically comes over to this. There are far more ways to interrupt things. Like all these peripherals have different ways of interrupting stuff. You still write an ISR, they still queue, but now you actually have 3 levels. So you can have a low-level interrupt, which interrupts your code, but a high-level interrupt can interrupt it. So it's just sort of priority, like the high-level interrupts will always interrupt the lower-level interrupts and not the other way around,
So
which can be useful.
Yeah, one good example is, let's say you're doing really fast serial communications, and so you make that a high priority, so as soon as that serial byte gets in, you do something with it so that when the next byte comes in, you're not going to overflow and lose information. Whereas your low-level interrupt might be your soft PWM with blinky LEDs, where it's going at about 120 hertz, and if it gets delayed a little bit, nobody cares. And then there's also interrupt behavior where you can end up with starvation and interrupts. It's probably not way beyond the scope of this class, but you can fiddle with some other stuff.
Okay. You get a DAC. It's not a misspelling of an ADC. It's digital to analog. So precisely like an analog to digital turns an analog voltage into digital bits that you can read in. This turns a register setting into an analog voltage. And it can do that at up to 1 megasamples per second and 12 bits. So very fast. So you can turn your gadget into a signal generator, like the benchtop signal generators you might find in an electrical engineering classroom, or you can record speech with ADC and then play it back with the DAC. You would hook this up to a speaker amplifier and drive a speaker, and it would play sound. And if you also hooked up an SD card, you could record gigabytes of sound and play it back, and now you've got an MP3 player. So yeah, there's lots of stuff you can do with this. Any other uses for DAC?
Voltage references for feedback loops. For something that wanted to have a voltage controlled oscillator, there you go, that's your variable voltage.
Yep.
That's very convenient. Okay, so DMA, this is a feature that you don't really ever find on an 8-bit microcontroller. I think anyone who does a lot of like electronics, computer engineering stuff already knows what DMA is, but basically it's direct memory access. It's, let's say, the most common stuff where it starts happening is when you've got a lot of data and you just need to put it somewhere else. So you say, I've got this audio file, I want to put it out on my DAC. If you were writing code that did that, you'd say, okay, it's now time to put the next voltage in my output buffer. Let me go read the next byte in the buffer, set the DAC to that value, and then I'm going to go do something else. But oh, it's now time to do the next one. So it's very CPU intensive, and so like it takes forever. And so what DMA lets you do is just say, hey, Mr. Memory Controller, please take, at some fixed rate, take the data from this bucket and put it over here. And that's all it does. It just does this in the background while the CPU is busy, adding up numbers, subtracting numbers, jumping around in the code. The data is just going where you want it. And basically, you have data, it's either an SRAM, it could be another one. You could take the data from an ADC and have it just slurped by the DMA and put it to RAM, so you could look at it later. So that you could say, hey, have you captured 6,000 samples yet? And the DMA says, sure I have. Here is your 6,000 samples. Then you do something with them, and then you start the DMA up again. You could have a serial port that data goes somewhere, or the serial comes from one serial port, and then you put it on your USB port, and you're acting as like a serial to USB bridge for some device. And this is where you basically start doing stuff, because generally, as long as you're only doing one thing on your microcontroller, you use the CPU, everything works great. When you want to do two things on the microcontroller, usually you use the interrupts, and if you're lucky, you don't hit 100% CPU utilization and everything looks great. But when you start trying to do more things, DMA makes your life much better. So any like real processor has DMA. Nowadays, like they do stuff where they just sort of preemptively fetch things in ways I don't even understand anymore.
I mean, basically, if you think of like, say you are sampling analog at 2 megasamples a second, that's a lot of samples. Your clock speed is 32 megahertz maximum. So you have 16 clock cycles in between each sample. And if you're trying to process any of that,